Okay, so this is our next video for Math 1560, Calculus 1 at U of L for fall 2017. We're continuing through Chapter 3 now, moving on to Section 3.2. And we're going to look at Rolle's theorem in this video. Rolle's theorem is sort of a precursor to the mean value theorem. Both Rolle's theorem and the mean value theorem won't play major roles for us. We need these results to establish a few basic facts about how the derivative gives us information about the shape of the graph. And once we've established those results, we're not going to come back to these results particularly often. You're going to see a couple of questions involving these results directly on your third written assignment, but aside from that, you're probably not going to see much in the way of, let's say, test questions involving Rolle's theorem or the mean value theorem. So let's see where Rolle's theorem comes from. Let's introduce the basic ideas before we state the result. So the basic idea in Rolle's theorem is that if you're dealing with the graph of a function, so each of these pictures here represents a graph, right? So the graph of some function. So these all represent y equals f of x for different functions f of x, and all of these graphs have a couple of things in common. Okay, so in each of these graphs, so this is some value a, this is some value b. In each of these graphs, we notice that f of a is equal to f of b. We also notice that, well, at least it looks like f is both continuous and differentiable in each of these graphs. And so we think about what can happen if you have a function which is continuous and differentiable, and it has to begin at the same y value that it ends. Well, one function that does that is a constant function. You just go straight across, like we see here, right? You just keep the same y value all the way across. Or, maybe you allow for a function that starts out kind of going up a little bit. So we start out, say here, we head up a little while. Well, if we go up a little bit and we need to begin at the same y value if we need to end at the same y value that we started at, well, then if we've gone up, we must then come down, right? And similarly, if we started out going down a little bit, well, then we're going to have to come back up a little bit if we want to end up where we started. And of course, you might go up and down more than once. So we might have something like this fourth graph here. But in each case, you notice that, well, I mean, in the first case, the graph is horizontal all the way across. But in each of the other cases, right, there's somewhere in that graph at least one point. There might be more than one, but there's at least one point where the tangent line is horizontal. And what do we know about points where the tangent line is horizontal? We know that those are exactly the places where the derivative is 0, right? So we know that if we've got a continuous and differentiable function that takes the same value at two different points, what this is telling us is that somewhere in between those 2 points, we have to have a critical point. This is what Rolle's theorem is saying. So the precise statement is, right here. So Rolle's theorem says, suppose we have a function, it's continuous on a closed interval, it's differentiable on the corresponding open interval, right? Usually when we talk about differentiability, we always talk about differentiability in the context of open intervals. And suppose that f of a equals f of b. So the beginning value is the same as the ending value, right? Well, then there must exist some point between a and b such that f prime of c equals 0. Okay. And so let me walk you through. I'm not going to do the whole proof, but let's just kind of sketch the proof. Okay. So we know because f is continuous on the closed interval, we know from the extreme value theorem that f must have a max and a min, right? It has to have a global maximum and a global minimum. And we know where those max and min values have to occur. They either have to occur at an endpoint or at a critical point, right? And these have to occur at either an endpoint or at a critical point. Okay. Now, of course, one possibility is that the max and min both occur at an endpoint, right? So if the max and the min, if those both happen at an endpoint, well, the function has the same value at both endpoints, right? That means that the max has to equal the minimum, right? It's the same value, if it's the same value at each endpoint and the max value is the same as the min value, well, the only way the max can equal the min is if you have the same value all the way across. So f is constant. And we know that the derivative of any constant function is 0, so in fact every c between a and b would work, right? Well, okay, so suppose that doesn't happen. Suppose that the max and min don't both occur at an endpoint. Well, then at least one of them has to occur at a critical point. And remember that we're requiring that f has to be differentiable. What are the two possible critical points? Either f prime is 0 or doesn't exist. But if f is differentiable all the way across, then there are no points where f prime doesn't exist. And so that must mean that there has to be a point where f prime equals 0. And that's more or less how you would establish Rolle's theorem. Once you fill in the details, this is why Rolle's theorem is true. Okay, so Rolle's theorem guarantees the existence of this point where the derivative is 0. It guarantees the existence of a horizontal tangent somewhere between the two endpoints, as long as we know that our function takes the same value at each endpoint. All right, so what can we do with Rolle's theorem? Well, the main reason we care about Rolle's theorem is because we're going to use it to prove the mean value theorem, and the mean value theorem has lots of uses. But what's some other things we could do with Rolle's theorem? Well, here's an example that's pretty similar to something you've got on your third written assignment. Let's show that this polynomial has exactly one real root. So how can we show that it has exactly one real root? Well, first of all, we know that, so if we let f of x equal 2x cubed plus 6x minus 1, we know that this is continuous. Why is it continuous? Well, it's a polynomial, and we know that every polynomial is continuous. Okay, so far so good. So we've got a continuous function. Sorry, that was some terrible handwriting. Getting used to a new stylus here. Polynomial. That's better. So we know it's continuous, and so one thing we can employ here is we can employ the intermediate value theorem, right? So we notice that f of 0 equals minus 1 is less than 0, and f of 1, well, that's 2 plus 6, which is 8, minus 1 is 7, is bigger than 0, right? And so the intermediate value theorem says that we must have f of c equals 0 for some c between 0 and 1. Okay, so now we know there's at least one real root. We found one, right? Well, we haven't found it, but we know it exists. This number c is one real root. F of c equals 0. How do we know that there can't be one more? Could there be one more? Well, let's say f of d equals 0, okay? For some d. Okay, and let's say that c is smaller than d. If c is bigger than d, we can exchange the roles of c and d here, and we can produce exactly the same argument. So let's just assume that c is less than d. We'll get the same story either way. Well, we know that f of c equals f of d, right? Because they're both equal to 0. We know that f is continuous on the interval from C to D, and we know that it's differentiable on the open interval from C to D. So Rolle's theorem says that we should be able to find some point between C and D where the derivative is 0. Well, what's f prime of x? F prime of x is 6x squared plus 6. Okay, so that is, well, that's 6 times x squared plus 1. This is always bigger than 0, right? Because we know that x squared is bigger than or equal to 0. So this thing is always at least 6, so it's definitely bigger than 0. So we know just by looking at the derivative that the derivative can never equal 0. And if the derivative can never equal 0, well, if there were two roots, we'd be violating Rolle's theorem, because Rolle's theorem says that there has to be a place where the derivative is 0 in between those two roots. We know that there is no such place where the derivative is 0, and so the only conclusion we can make is that since the derivative can never equal 0, there can't be a second root, or we would be violating Rolle's theorem. And Rolle's theorem is well established. It's definitely 100% true. There's no gaps in there. We haven't found a counterexample. Right? What we found is, well, there's no way to get that second root without violating Rolle's theorem. We're not allowed to violate Rolle's theorem, and so there must not be a second root. There's only one, and that's what we needed to show.